angular and linear speed. When it comes to motion of something that is able to rotate, there are, as the title suggests, two different things that we might be looking at. So if we draw a little circle here and think about it as rotating, well, first of all, the angle at which it is rotating is an interesting thing to track. And that's a useful thing to track because in rotation, points near the center are going to be moving slower and points near the edge are going to be moving faster so that the wheel stays in one piece as it rotates. And that's the other thing we need to track. If we're looking at, say, a bicycle wheel or the tread of a car tire, then the thing we care about is the outside edge of the shape. But we could just as easily be worried about some piece in the middle and thinking about how fast is that piece going in a linear sense. So we know that arc length is the radius times the angle. And we know that the speed that something is moving is the distance that it goes divided by the amount of time that it takes. And by substitution, that means that the speed at which a point is traveling is its radius from the center times the angle in which it rotates divided by the time that it takes to get there. And I'm going to separate out this theta divided by t, the change in angle divided by the change in time. And what I'm going to do is simply name that quantity. The thing is called the angular speed, and the character that we usually use for angular speed is the Greek letter lowercase omega. You may be familiar with the capital omega. It looks like that. It's the unit of resistance in electronics. But the angular speed, lowercase omega, will be the angle divided by the time, just because that's a nice substitution in here. So we can translate from linear speed to angular speed exactly the same way we translate from linear motion and angular motion. So with that in mind, let's take a look at an example. A cyclist is riding a bicycle whose wheels have a diameter of 30 inches. If the cyclist is riding at 17 miles per hour, find the rotational speed of the wheels in revolutions per minute. So we have this diameter of 30 inches, which means that the radius would be half of that, or 15 inches. We have that our linear speed, v, is 17, and that's in miles per hour. And it's the angular speed omega that we're looking for. And we need our angular speed to be in revolutions per minute. So on the surface, this is a fairly straightforward calculation. We're simply going to say that v is r times omega. So omega is v over r. The problem is that when we substitute in, we get miles and inches, and that's a problem. But in theory, these are the right units, and we just have to try to figure out how to get from these units to the units we care about. So I'm going to go ahead and grab this line because that's really the only part of this we still need, and go to one more slide so I have some room to work. All right. So I want to take 17 miles, and I know that 1 mile is 5,280 feet. And I know that 1 foot is 12 inches. So miles will cancel out and feet will cancel out. And I get here the nice, easy to work with number that 17 miles is 1,077,120 inches. So omega is 1,077,120 inches over 15-inch hours. The inches will cancel each other out. And if I take 1,077,120 and I divide by 15, I get 71,808. And my units are 1 over hour. Starting to get somewhere. Still have some more room to go, but we're starting to get somewhere. Now, thinking about what I'm dealing with here, omega is the angular speed, the change in angle divided by the change in time. So here's where I take advantage of that thing I know in the back of my mind, that whenever I'm talking about an angle and there are no units, I'm really talking about radians. So this isn't just 1 over hour. This is given in radians per hour. Again, radians are a unitless measure. We don't have to write that this is in radians, but making note that there are radians involved, we're talking about a change in angle, will help us figure out what the next step is. Because the problem asked us to find this value not in radians per hour, but in revolutions per minute. So we have a little bit more to do in the way of unit conversions. I need to get from hours to minutes, and I need to get from radians to revolutions. To cancel out the hours, I know that 1 hour is 60 minutes. And if I set that up in this format, the hours will cancel each other out. And if I take 71,808 and I divide by 60, I get 1,196.8 radians per minute. All right, starting to get a little bit closer. what I'm looking for again was revolutions per minute. So as one last step, I will remember that one revolution, one complete circle, is 2 pi radians. So I will take my 1196.8 radians per minute, and I will multiply that by one revolution over 2 pi radians, so that the radians cancel each other out. Again, I know radians aren't really a unit. I don't have to be writing anything there, but it helps me visualize. So if it helps you visualize, let's keep with that. Careful punching this into your calculator. Remember, divide by 2 pi in parentheses to make sure that everything works out. But I'll just take that, I'll divide by 2 pi, and I don't know, round to the nearest tenth of an RPM. 190.5-ish revolutions per minute.